All right, so got a lot to go through today. I'm going to try something a little bit different with you guys, I think, to make this point. So we're going to kind of finish hypothesis testing. We've got two other types of examples that we haven't talked about yet, which we'll go over today. We'll work through a bunch of problems, and we'll probably do a lot of hypothesis testing during the review on Monday for next Wednesday's exam. I'll say next Wednesday, right, the 30th. Okay. So one thing that you'll see in some of the slides, and we'll kind of ignore, we're not even going to look at the slides, we'll just go past them, but also on the practice exams, and I mentioned this a little bit on Wednesday, anytime you see things with critical values, we're not going to do anything with that, okay? So we're going to hold off on that discussion until after the exam. So we're just going to focus on p-values and making rejection decisions with those for the upcoming exam, okay? So anytime we see critical values, you can kind of ignore those. I won't expect you to know how to do that. We're not going to cover it before this exam, okay? But we are going to have to know how to do hypothesis testing with p-values. And so we'll kind of pick up on an example where we left off, and then I'll kind of introduce the next two types of examples we could have. So this has, I don't know, some group states back to school spending, averages $606.40. A researcher expects that it's different from this amount. So right away, what would our null and alternative hypothesis be? Well, we want to know whether or not back to school spending is different from or differs from this value of $606.40. So anytime we see this term different than, we should automatically be thinking we have a two-tailed test. So why? Well, if I want to test for whether or not this true population mean is anything different than $606.40, what I'm really saying is I want to test to see, is it not equal to that value, right? So not equal to sign in the alternative hypothesis means we have a two-tailed test. If I then want to identify the null, well, it's just the complement of that. So if I want to test for whether or not it's different than $606, I'll assume it's exactly equal to that. And I may drop off, I probably won't be saying the decimals here just for the sake of not getting too wordy. So that's kind of our setup. Excuse me. The next thing we'll do is just identify the information given to us. So we've got a sample size of 30. We find a sample mean for back to school spending of $622.85. Whoops. And then we're given this known population variance. So in practice, this isn't as likely, right? It's likely we only have a sample variance, and we'll go through those problems by the time we're done today. But for now, we're going to kind of work off on where we're given a known population. So at this point, we can kind of think about, okay, I have this sample mean. What should the distribution of my sample means look like? So I've got my sample means. They should be centered around the true population mean, but I don't have that, but I am assuming that it's equal to a certain value, right? So I'm grabbing that value from my null alternative hypothesis, right? That's the assumed true value of the mean. We see $622.85. So we want to find the probability that we saw something that was as inconsistent with what we assume to be true, or anything even more consistent. Now the issue is here, we said originally we have a two-tailed test. So I've got one of my tails here. Well, it would have been equally as likely for me to see sample evidence on the other side of the distribution that was just as far away. And those values would also go against the null, right? Because now evidence on either side goes against the null, right? So I only see one sample, right? One sample mean. I can find the probability that I saw something that inconsistent or even further, but it would have been equally as likely for me to see something that went against the null on the other side as well. So once I find this area, we said the additional step with a two-tailed test to get my p-value, I then have to multiply it by 2. And if this is, I don't know, multiply whatever, sign is. Okay? So it doesn't look like 0.2, I guess. That's what I was trying to do. So, how can we do this, right? Well, we've got a normal distribution. We should be able to turn that sample mean value we found into a z statistic, right? Or into a z value. Okay? Now, what's the equation that we had for this? So that was where we just take our sample mean value. We usually subtract the true population mean, but here all we have is an assumed true mean. And then we'll divide by the standard deviation of our sample means, which we could calculate this ahead of time or just do it all at once, right? So that's the square root of our population variance over our sample size. So when it comes to these test statistics, Z statistics, it's really just a matter of plugging the values in that we were given and doing the computation. So here, my sample mean was what? 622.85. The assumed true mean, or the value that comes from our null, was 606. And then divide by what? 4,225 over my sample size of 30. At this point, it's just a matter of getting this entered into my calculator. Now, just like with confidence intervals, I think one thing that makes this a little bit easier is you can calculate this denominator ahead of time, and then you just have one value to plug in, right? So trying to do this all at one time, you got to make sure you're getting parentheses here. It's a little bit easier. Just calculate this value ahead of time. Like add in this intermediate step, just like we did for confidence intervals. You don't have to, but I think it makes it so you don't make any easy kind of computation errors in your calculator. Okay. Any questions up to this point? And you'll have this. This is on that formula sheet going into that exam. Okay. So I think, let me see. I think this is 1.39. We'll see if I can't remember. It's on this slide here. So, yep. If we plug all that in, we get 1.39. Okay. So we're not done, right? I wanted the area to the right here. If I look this value up in my table, the table tells me the area to the left, right? It always gives me the cumulative probability. So I would then have to subtract that from 1. Now, that's going to give me the area in this right tail. So once I subtract this from 1, I still need to multiply it by 2 to get my total p-value, okay? Because it's a two-tailed test. So I'm going to go to my standard normal table. And I'm going to look up 1.39. Well, that second decimal 9 is over here on the very far right. 1.3, 0.9177, right? So we're still looking up these areas the way we had them before. So 0.9177. Now here, if you made a mistake and you forgot to subtract it from 1, and if you're like, oh, but it's a two-tailed test, I have to take this and multiply it by 2. I'd get what, like 1.8 something? Well, right away, you know that you forgot, you made a mistake because your p-value represents a probability. So it has to be between 0 and 1. So if you had just taken 0.91 multiplied by 2, I got 1.8. I get something wrong. Oh yeah, I had to find the area to the right. The table gave me the area to the left. So I subtract that from 1. It's what, 0.0823. And then I'll multiply that by 2 to get my total p-value because I have two tails with a two-tailed test. Right? So I think if you do that, you should get 0.1646. Okay. Any questions over anything we've done up to this point or any of these steps? Okay. So we've got our p-value, right? Now, the whole reason we're doing this is to see, can we reject the null hypothesis? So my p-value, the only time I reject is if it's less than alpha. So I've got what, 0.1646 here. And I can test against, 0.10, 0.05, and 0.01. Kind of our typical benchmark alpha values. They would correspond to the 90, 95, 99% confidence levels. And then we'll start using this terminology, which is significance level. So we won't harp on it as much when we're thinking about hypothesis testing, although we will use it. We're really going to use it once we get to linear regression. So all the significance level is, so being able to reject at certain levels of confidence. We can also say a slightly different way, which is we reject at certain levels of significance. And the significance levels are just basically the percentage form of alpha, right? So 10, 5, you kind of think about all these here are percentages. Okay? So the 10, 5, 1% significance levels correspond to the 90, 95, 99% confidence levels. Okay? So which of these can we reject the null hypothesis at? Is 0.1646 less than 0.1? No, right? So I kind of fail to reject here. Well, if it's not less than 0.1, well, then it's definitely not less than 0.05 or 0.01, right? Or think about it differently. If I can't reject it at 90% confidence, how can I reject it with 95%, right? I can always, I can't say something with 90% certainty. How could I say it with 99% certainty, right? So as soon as we kind of find a failure, we know that every alpha smaller than that, we would fail at as well. In fact, what the p-value really is telling us is like the last level or the last alpha for which we would reject the null at. So think about it this way. If instead we had alphas of like 0.2, well, it's gonna be less than that. Well, what about an alpha of 0.18? It's less than that. In fact, we kind of keep going. The last one that we would reject it is like what? No, I want 6, 0, 0, 0, 0, 0, like 1, right? And that would just barely be right. So I could kind of, the last alpha I would reject that would be just slightly above whatever my p-value is. My p-value is essentially kind of like the last alpha I could reject for the null at. Okay. Any questions there before we keep moving? Okay, so here's where I'll do something a little bit different than I did with the first section. We'll see. I think it'll work out a little bit better. Okay. So let's look at the same information, just a different order. So we have hypothesis testing for the values of the population mean when we were given a known population variance, right? That's how we calculated that Z statistic. So more broadly, right? And I keep accidentally saying it, but a more general term for the Z statistic is a test statistic. Now, the reason why we call it a Z statistic is because it's a test statistic coming from or representing a Z value from that standard normal distribution, right? So we'll call this like a Z stat, right? Or a Z statistic. Well, we're going to end up, I'll show you in just a second. We also have T statistics, right? That come from a student T distribution. They're both test statistics. It's just that they're test statistics from different distributions. Right? In fact, there is one, we won't use it in this class, but like there's even an F distribution, which we call it like F stat, right? So like add an S and like F stats, right? So we've got like all these distributions. We can have test statistics from them. So we're just going to call it whatever the distribution is, statistic, right? But they're all test statistics. So let's think about if we wanted a test statistic for a sample proportion. So we did this hypothesis testing for sample means. We can also do it for sample proportions. It's just instead of assuming that the population mean is greater than or less than or not equal to a certain or equal to a certain value, we assume that the population proportion is less than, greater than, or equal to a certain value. Okay. So when we do this, it's going to be the same setup that we had when we were looking at the distribution of our sample proportions. So we'll take our sample proportion value that we see, just like we took our sample mean. Now, generally, the equation that we had was we would subtract that population proportion. And then down here, remember, our denominator represents the standard deviation of the statistic we're looking at. And the equation that we had for the standard deviation of our sample proportions was that population proportion times 1 minus it over our sample size. But here, I don't know the population proportion, so what do? Well, I didn't know the population mean, so I was using that assumed true value. So in here, I'm going to be using that assumed true population proportion. That value is going to come from my null alternative hypothesis, just like that assumed true population mean came from my null alternative hypothesis. But this is the only difference. All the other steps, exactly the same. The only difference when we're dealing with proportions is going to be when we have to turn them into that Z statistic. Okay? But in terms of identifying the null alternative, looking up p-values, everything's going to play out exactly the same. And we'll work through an example here in just a second, but I wanted to kind of show you this test statistic. Hopefully you can kind of see where they're lining up. Right? The other type of example that we'll work through today is when we have a sample mean and we want to do we want to do hypothesis testing for the population mean, but we don't have this known or this given population variance. All we have is a sample variance. So just like with confidence intervals, if we only have a sample variance, we said we had to do what? So if I didn't know the population variance with confidence intervals, the only thing that really changed was that I had to use the student t distribution, right, as opposed to the standard normal. Same thing is going to apply to hypothesis testing. So here, and I'm just using subscripts to identify like this is a z-value for a sample mean, a z-value for sample proportion. But now when I only have a sample variance, then I'm going to have a t-value. Right? I have to use that student t distribution. I'm going to end up with a t statistic instead of a z statistic. It's a little bit semantics there, right? They're both test statistics. We're just identifying what distribution they come from. So we're going to set it up exactly the same, right? We'll take the sample mean value we found, subtract the assumed true mean. Now here, when I'm dividing by the standard deviation of my sample means, just like I did before, but we use slightly different notation because now all I can do is use this sample variance. I don't know the population variance, right? So our test statistic equations are going to be a little bit different, and they represent something coming from a student t. But once again, other than that, all the steps are the same. Right? So we're going to start doing some proportion stuff so we can keep using that standard normal distribution. And then we'll kind of finish looking at some examples where we only have a sample variance. How do we find p-values using that student t distribution? Any questions over anything there before I keep moving? Kind of give a little bit more of a roadmap and kind of work on stuff. Okay. Let's go back to the slides here. And I kind of already went through, we kind of thought about, we could look at different alpha values if it was a p-value less than it. So here we're doing hypothesis testing for proportions. Like I said, it's the same exact thing. So we've got left, right, two-tailed tests, right? And we still identify the type of test based off the alternative hypothesis. It's just now I've got assumed true values for the population proportion as a, opposed or compared to assumed true values for the population mean. Right? Makes sense. That's a statistic I'm interested in. So the steps are going to be exactly the same, right? You can kind of ignore the critical value step. Instead of finding critical values, we're going to keep using that test statistic or that z statistic to find a p-value and then make a rejection decision. We're holding off on the critical value stuff until after the exam. Okay, so these will be our kind of steps, although instead of finding the critical value, we'll keep using the steps that we had been, which is to find the p-value and then compare the p-value to alpha. Okay. And I kind of already mentioned here, the reason why we're using the assumed true proportion in our denominator is because we really should be using the true population proportion, but all we have is the assumed true value. Okay. We'll skip the critical value stuff. Keep going. There we go. I'm going to skip this example because I don't think it's as interesting. I want to make sure that we go through, we use our time wisely. Also, I had it set up so it's kind of goofy. I might do that example on Monday to make a point, but I might just hold off and try to make that point after the exam. So we've got this set up, right? We're looking at Indiana birth data again, and I've got 72 of 400 mothers smoke while pregnant. So if I want to know for what a test for whether or not more than 15% of mothers, sorry, I don't know. So we want to test for whether or not more than 15% of Indiana mothers smoke while pregnant. So what would my null alternative hypothesis be here? All right. So I'm wanting to test for whether or not more than 15% of Indiana mothers smoke while pregnant. And so that is going to be my alternative hypothesis, what I'm going to test for. Right? So here, I want to see, is that proportion greater than 0.15? So I assume the exact opposite is true, which is that it's less than or equal to that value. Now here, I've got my sample size is 400, but maybe a little bit trickier. What's my sample proportion? So I'm not directly given it here, but if I wanted the sample proportion of Indiana mothers who spoke while pregnant, and I found 72 of the 400 mothers in my sample smoked while pregnant, what would I do there? Yeah, right. So really we said this is kind of like the number of successes or whatever you're looking for over the number of trials, or in this case, kind of our observations. So it's really just 72 over 400, right? 72 out of the 400 Indiana mothers smoked while pregnant. Okay. So I think this works out to be 0.18. Any questions to this point? All right, so what we're thinking about now, instead of the distribution of sample means, is the distribution of our sample proportions. Well, we said those should be centered around the true population proportion, but we're using an assumed true value for that, so 0.15. We've got a sample proportion of 0.18. And I don't think I asked this, I might have said it, but what type of tailed test do we have here? So we always look at the alternative hypothesis. I've got a greater than sign. So I've got a greater than or a right-tailed test. Only evidence on the right-hand side of this assumed true value is going to be something that supports the alternative and goes against the null. So we got a right-tailed test. Then my p-value is going to be the probability I saw the sample statistic I did that was as inconsistent with what I assumed to be true as what I found, or anything even more inconsistent. So for a right-tailed test, that's going to be the area to the right. So this represents my p-value. Well, what's the next step? I can find my z-value for this sample proportion. Once I do that, I then want the area to the right. Well, how do I find this z-value? Well, we have this from our formula sheet, right? We're going to have that going into the exam. I'm just plugging my values in here, right? So my sample proportion is what? 0.18 minus that assumed true proportion of 0.15 divided by, let's see if I can get this to stay here while I write, the square root of the assumed true proportion times 1 minus the assumed true proportion over my sample size, which represents that standard deviation of my sample proportions. So here my assumed true proportion is 0.15, and my sample size was 400. Oops. Any questions there on kind of the setup? I mean, really, these test statistics, I want to say they're like should be easy questions in a sense, but like you're going to have these three formulas on the formula sheet. I mean, just the notation that I use, hopefully you can identify when you've got a proportion. I mean, generally I'm using the terminology of proportion and I'm giving you like, you know, p hat is equal to this or something. So I try to make it easy, like to know when you need to use which equations, right? I'll tell you, whether you have a sample variance or a population variance, and I'll often use I'll use the words, but I'll also use the notation, right? And so here it's just a matter of getting our values plugged in. So if I do this, I don't remember what the value, I think it's 1.68. So we'll skip the critical values. Yeah, so 1.68. Let me see if we plug everything in here. And like I said, one thing that might be worth doing, calculate your denominator ahead of time, make your life easier. That way you just have one value to plug in here. Also to not worry about parentheses. If I look at this, I can do that mental math in my head. So just use 0.03 instead of, maybe, worrying about using parentheses in my calculator. So, whoops, we got our test statistic or our Z statistic. So this is 1.68. So when I look this up on my standard normal distribution table, the table always gives me the area to the left, right? Or a cumulative probability. Probably I see that Z value or anything below it. Well, I wanted the area to the right, that represented my p-value, so I need to then subtract it from 1. So for a right-tailed test in practice, you're going to find the area to the left. You then have to remember, well, I wanted the area to the right. I need to subtract it from 1. And, if you're trying to do this, and remember it all, I'll tell you, when I work through these examples, when I write exam questions, I'm always drawing out pictures just so I have something to kind of visualize and be able to keep track of what I'm doing. And I don't forget steps like, oh yeah, I had to subtract from 1 because I wanted that right tail. Okay. So we can go to that standard normal distribution table. We got what, 1.68. So that second decimal is here, this column. So keep my mouse there so I don't lose it. 1.68. So 0.9535. Right? So that's going to be the area to the left of that Z value. So the table told me the area to the left was 0.9535. Okay. Well, I wanted that probability of seeing something above the sample proportion that I did, or above that Z value, that Z statistic. So I then need to subtract this from 1. And right, my p-value is about 0.0465. Any questions on that before I move to the next step? Because we're almost done. Right? We've got everything that we need. We've got our p-value, but we then need to make our final rejection decision. Right? Based off of the probability of seeing what I did, can I reject what I assume to be true? Because it was inconsistent with the null. It was inconsistent with what I assumed to be true, but wasn't inconsistent enough. Well, the probability of seeing it was about 0.04. So when we set these threshold values for alpha of 0.1, 0.05, and 0.01, what we're really saying is we're okay rejecting that null hypothesis if the probability of seeing our sample statistic falls below any of these levels, right? Or, depends. If we wanted to do 90% confidence or 10% significance or 99% confidence, right? But we can test against all three, right? As long as we're testing against one, it's pretty easy to test against all three. So if we kind of just remember our confidence levels, 90, 95, and 99, just like how we were doing with confidence intervals. Right? And then now we've got these significance levels, which are just alpha, but in percentage form. Okay? So my p-value was 0.0465, I believe. So 0.0465. You don't have to write this down 3 times. Just I'm doing it to make it kind of easy to see that comparison. Is 0.04 less than 0.1? Well, it is. So I can reject with 10 at the 10% significance level or with 90% confidence. Is 0.04 less than 0.05? Well, not a whole lot, but it is less than that. So I can reject at the 5% significance level as well, or with 95% confidence. So I can reject with 90 and 95% confidence or at the 10 and 5% significance levels. But is 0.04 less than 0.01? No, it's not. Right? It's greater than that, actually. So I would fail to reject the null with 99% confidence. Okay. Any questions over that process? So kind of remember this p-value represents the probability that I saw the sample evidence that I did, right? If what I assumed to be true was in fact true, right? And if that probability starts to fall, it gets too low, then probably what I assume to be true isn't true, and I'm okay rejecting it. Well, here the probability is relatively low, 0.04. So I rejected that null at the 10 and 5% levels with 90 and 95% confidence, but it wasn't inconsistent enough with what I assumed to be true to be able to reject the null with 99% confidence. Okay. Any questions there before we move on from this? So I'm going to jump from proportions to examples where we only have a sample variance so we can get some practice today using that student t distribution. And I'll probably revisit some examples of proportions on Monday while we're doing a review. All right, so let's see. Here we go. So once again, we kind of ignore this critical value stuff, but I want you to be able to see that test statistic. I already showed you this ahead of time. I said, the more realistic examples when we're doing hypothesis testing for what different values of the population mean are that we only have a sample variance. Nobody gave us this known population variance. If we didn't know the population mean, how the hell do we get the population variance, right? So we're going to be using this as our test statistic, and everything else is going to be the same, except we have to use the student t distribution to find our p-value, right? We can't look up a t-value on the standard normal table. We have to look it up on that student t, right? So I'll show you a couple issues with this and then mention how I'm going to do it differently on the exam to make it a little bit easier. Okay? So the first example we have is home prices in Muncie. So I think this was like 2018 when I pulled this data, but let's say you want to test for the hypothesis that the average home value in Muncie is different than a value of 90,000. Right? So different than, anytime I see this term, I should be thinking I have a two-tailed test. I want to test for whether or not it's different than or not equal to this value. So I want to test for, is this population mean different than the reported amount of 90,000? Which means the null hypothesis is that I assume the exact opposite is true. So there will be questions on the exam for you to identify a null and alternative hypothesis from a problem like that. Really it's whatever you're trying to test for. The problem is going to give you what you want to test for, what you're trying to find. That's your alternative hypothesis. You then assume the opposite is true, and that's your null. Okay. So we've got, I think I already mentioned this, but I've got a not equal to sign in my alternative hypothesis. So I've got a two-tailed test. Now the rest of the problem, I believe, says, we take 51 homes. So I'm just going to jot down what I'm being given. So sample size of 51. And I find an average home price of my sample of 85,000. And then my sample variance is 100 million. So that was just everything I was given from the problem. And I know that I have a two-tailed test. So the next step, just to kind of have a nice visual, is think about, okay, what does this distribution of my sample means look like? Well, it should be centered around the true mean, but I've got an assumed true value for that. So I'm going to, if I assume that the mean is 90,000, then they should be centered around that, if that in fact is true. Well, I saw this sample mean of 85,000 over here. Now, if I'm thinking about eventually I want to find a p-value so that I can make a rejection decision, the p-value is going to be the probability I saw the sample evidence that I did, right, that was as inconsistent with what I assumed to be true as what I found, or anything more inconsistent, or anything kind of further into the tail, any values kind of larger in absolute value. Not larger in absolute value, sorry. Any values that are further from that assumed true population. However, I've got a two-tailed test, so it would have been equally as likely for me to see something that was 5,000 away, but on the other side, or anything even further than that. So once I find this area, I still need to then multiply it by 2 in order to get my p-value. That's just the setup, right? So what's the next step? Well, usually we would turn our sample statistic into a z-value, but here I've only got a sample variance, so I have to turn it into a, t-value. And then I can think about, I've still got two tails over here. So at this point, it's just going to be a matter of, okay, we've got those test statistical equations that we outlined earlier. I just got to plug in the values I was given earlier, because it's just computation at this point. So I'll take my sample mean, which was 85,000, subtract that assumed true mean of 90,000, and then I'm going to divide by the square root of my sample variance, which was what, 100 million, over that sample size of 51 homes. Okay. Any questions here? Okay, so this was actual kind of data. I'm going to show you something a little bit different. So if we calculate, I think it's negative 3.57 if we plug all those values in. So negative 3.57. I'm going to work, what's the easiest way to do this? The way that I'll typically do this on the exam is once we have this test statistic, like the next question, if I then ask you for the p-value, well, if you got the test statistic wrong, you're probably going to get the p-value wrong. So I then give you an assumed true value. So let's say instead of negative 3.57, I'm going to cheat here. Let's see if I can remember it. 2.4, yeah. So let's say that instead, let's say instead of this worked out to be negative 2.403, just to have a better number to work with. I would give you that assumed true test statistic so that you don't have cascading errors. So if, and this is, it should be negative 2.403. So I can find the area to the left of negative 2.403, just like if I had used the actual test statistic, but this number ends up being a little bit clean. So negative 2.43, I'm going to go to my student t table. But before I do, oh shoot. What's something else that I need if I'm dealing with a student t distribution? Well, there's a bunch of different student t distributions. So we needed our degrees of freedom, right? Just like for confidence intervals. So n-1 our degrees of freedom is 50, okay? So negative 2.403 is our test statistic, and our degrees of freedom is 50. So when I go to that student t-table, my degrees of freedom is 50 here. But the problem is I only have 6 different t-values that I can look up, right? This t-table is a little bit restricted. Now, after the exam, we'll take a look at how we can do this in Excel. And there we're not limited, right? We can do anything because it does like the integration for us. But here, we've only got 6 different values that we can look up. Well, I gave you an assumed true statistic that ended up being one of these values because that's what I would do in the exam, right? I'll go through in just a second. If it wasn't, we actually would only be able to put the p-value in a certain range. But on the exam, if I give you a problem where you have to look a p-value up from a student t-distribution, it'll be one of these exact values that you can find in the table. So in this case, I gave you the assumed true test statistic of negative 2.403. That is a value right here. Now it's not negative, but how can I use the student t-table to still find the area to the left of negative 2.403? Well, the table just always gives me the area to the right, so it doesn't have to have a negative sign in front of everything. But this is a symmetric distribution. So the area to the right of positive 2.403 would be the exact same as the area to the left of negative 2.403. So I can just use that 2.403. The area to the right of that is 0.01. So I know that here this area is 0.01, which means the area over there would have the exact same probability of occurring. So if you have a negative test statistic and you're looking at the student t-distribution, you just have to remember, I'm just looking up that value, but positive, and it's a symmetric distribution. So the area to the right of the positive value is the same as the area to the left of that same negative value. Okay. Now remember, we started this out, we had a two-tailed test. So if I know that there's 0.01 in each of my tails, well, I can think about it as just add those together, or I take the area in one tail and multiply it by 2. So here my final p-value would be what? 0.02. Okay. And then we can determine our rejection decisions, right? Whether or not this is less than our threshold set of alpha. Now, the reason why I would give you an assumed true test statistic here, like 2.403, let's say it was, like we use the actual test statistic of negative 3.57. The issue is, we're doing this by hand, degrees of freedom of 50, that value isn't on the table, right? But here I know that the area to the right of 2.678 is 0.005. So that would mean the area to the right of 3.57 would be less than 0.005. That's all I can say. I just know that it's closer to 0. It has to be less than that 0.005. So all I could really do there, if I use my actual test statistic, would be to say something like, well, I know the kind of area that I had here is less than 0.005. That was a two-tailed test, so I know the other tail is also less than 0.005. Probably an easier way to think about this, if both of these are less than 0.005, the total of them has to be less than 0.01, which really you could do by just multiplying whatever that range cutoff is by 2, just like you would for a regular p-value. But I won't make you kind of find a p-value within a certain range on the exam, but in practice and kind of after the exam, we might run into situations like this. On the exam, I will give you numbers that work out, or I will give you assumed true test statistics to be values that you can find exactly in that table, okay? Questions there before we keep moving? So let's use that p-value of 0.02. And then the next question that I maybe would ask is, what levels can we reject at, right? So my p-value is 0.02. We can compare to kind of our conventional alpha values. And if it's less than alpha, we said that we reject. Okay. So is 0.02 less than 0.1? Yeah. So I can reject at the 10% significance level or 90% confidence, right? Is 0.02 less than 0.05? Yeah. So I can reject with 5% significance or at the 95% level. Is it less than 0.01? No. So I fail to reject at the 1% significance or the 99% confidence level. So that's kind of how I'll make my rejection decisions. Is that p-value less than alpha? Like, just remember this, right? This is our rejection decision. Okay. Any questions on that one before we go to another example? Okay. So we've got a couple two-tailed tests in here, but let's say instead that I wanted to do something different. So go back to this Indiana birth data, and I've got, looking at the weight of the baby. So I'm just going to write down what we were given before identifying the null alternative hypothesis. So I take a sample of 400 births, so I know my sample size. I find this sample mean birth weight from that sample to be 3,132, and I calculate this sample variance. That's all I have. I wasn't given a known population variance. It's like 439,000. Okay. So what I want to test for is whether or not women who use alcohol during pregnancy have a birth weight less than the national average of 3,287. So what I'm trying to test for is my alternative hypothesis. And I'm wanting to test for whether or not that population mean is less than the national average of 3,287. I then have this null hypothesis, which is the exact opposite of that. So I assume that it's greater than or equal to 3,287. So what type of tailed test do I have here? Yeah, so I got a less than sign in my alternative hypothesis. So we've got a left tail test. So I can think about what does the distribution of my sample means look like? Well, it's going to be centered around this assumed true value of 3,287. I then saw a sample mean of 3,132. And my p-value, right, which I'll use to make rejection decisions, well, it's a left-tailed test, so it's just going to be the area to the left of that sample mean. Or the probability I saw the sample evidence that I did that was as inconsistent with what I assume to be true, or something that's even more inconsistent with that assumption, right? So anything further into that tail. And like I said, if an easy way to remember this, like right tail test, I'm looking for the area in the right tail, left tail test, area to the left. So the next step is I need to turn that sample mean into a test statistic, more specifically, a t statistic, right? Oh, I forgot to blow this up. Sorry about that. A little bit easier to see here. So I go back to what we had earlier, which was all these different test statistic equations. And I'm just going to plug in my values. So my sample mean is what? 3,132. The assumed true mean I was using was that 3,287 from that null alternative hypothesis. I'll then divide by the square root of my sample variance, so 439,907 over that sample size of 400. Okay. So I'm just plugging those values in. Now, like I said, I think this makes this a lot easier problem. Make this calculation ahead of time, then you just have one value to plug in there for the denominator. Okay. If we do this, we get like a wildly large test statistic, which is, I think it's like negative 4.68. So once again, here, I can't find that value in the student T table. I would give you an assumed true test statistic at the next step, which would be a value that you could actually find. Right? Yeah. Yep. So I would like ask you calculate the test statistic, and then the next question would be, what's the p-value associated with the test statistic? But at that step, I would say, assume that what the test statistic you found was 2.34, or whatever it is. Then what's the p-value? Yep. And the practice exams kind of have that, so you'll kind of see I give like these assumed true test statistics along the way. So I can't actually find this value, but if I did want to put this one, like come up with the range, just to make this point, if I look at that T table, well, my degrees of freedom here would be what? My sample size was 400. So n minus 1, 400 minus 1 would be 399. This is also an example. I was trying to use some actual numbers to kind of have some interesting examples. But this is one that I also wanted to point out. I won't do this to you on the exam, right? Because I can't find exactly 399 here. I'll keep all those degrees of freedom 80 or below, or I guess 80, 60 or below, so that you can find exactly your degrees of freedom on here, right? There's big jumps here, which we're doing this with a physical table. Once I go to Excel, I can do any degrees of freedom that I want. But for the sake of this upcoming exam, and for kind of using this table, I won't give you anything that's not here on this left-hand side as the degrees of freedom. Okay? So let's just, for the sake of this example, assume that our sample size is a little larger and that we could find exactly our degrees of freedom here, and maybe it was 500. Well, I would then go over and say, okay, well, at 2.586, the area to the right of that is 0.005. Right? So what's going to be the area to the right of 4.68? Well, it's going to be just even closer to 0 or less than 0.005. Right? Now, I was dealing with negative values, so I could still use this table, but I was just ignoring the negative sign. I was going to say, you know, if this stuff is true about the right side of the distribution, it'll also be true about the left. It's symmetric. So all I could really say here is that my p-value is less than 0.005. That's all I can say. Right? Once again, on the exam, I would have given you probably an assumed true test statistics that you could actually find. It would have been one of those 6 values in the table there. Okay. So you kind of see for a left-tailed test, it's like a lot easier. I don't ever have to like worry about subtracting from 1. I have to multiply into my 2. It's just whatever value I find from that table, that is my p-value for a left-tailed test. So left-tailed tests are probably the easier ones. Any questions over kind of anything from this problem? So we got a little bit of taste of every different type of problem we could see. When we have a sample mean and a known population variance, sample mean, but we only have a sample variance, and then also proportions. So we'll work through, do some exam review on Monday. I'll answer your questions first if you have them, but I'll probably try to focus just doing more hypothesis testing problems. I might even do some of the ones off the slides here. I'll bring in some additional ones that I have ready to go, or we can do some of the ones that are on the sample, on the practice exams if you have questions over that. So I think the last thing I have here, to work through these examples, kind of leave you with, well, once again, we can ignore the critical value approach. We're only going to use this p-value approach, okay? So I'll leave you with this terrible statistics meme, which is, hey girl, I made a type 1 error. I shouldn't have rejected you, right? Because type 1 error, you reject when you shouldn't have. Maybe just leave off the last part. Say I made a type 1 error. If they don't get it, then, well, maybe you didn't make a type 1 error, right? So have a good weekend. If you have any last minute questions on that Excel homework, I will be working a little bit this afternoon, but I'll probably be in and out of my office. So if you send me an email, I can try to get you a response to that this afternoon. Other than that, good luck with you. Just kind of start preparing for this exam, and I'll see you on Monday.